In this video, we will study the mappings on vector spaces that preserve their structure to allow us to define the concept of a coordinate. Earlier in our study of linear algebra, we said that vectors are objects that can be added together and multiplied by a scalar, and the resulting object is still a vector. Consider two real vector spaces V and W. A mapping phi from V to W preserves the structure of the vector space if phi of x plus y is equal to phi of x plus phi of y, and phi of lambda x is equal to lambda phi of x for all x and y in the vector space and lambda a real number. Here's a definition. Let V and W be real vector spaces. A mapping phi, taking V to W, is called a linear mapping if for every x and y in the vector space and real numbers lambda and psi, we have phi of lambda x plus psi y equals lambda phi of x plus psi phi of y. It turns out that we can represent linear mappings as matrices, and we'll see that later on. Recall too that we can also collect a set of vectors as columns in a matrix. So when working with matrices, we have to keep in mind that the matrix represents a linear mapping or a collection of vectors. Consider a mapping phi from V to W, where V and W are arbitrary sets, not necessarily vector spaces here. Then the function phi is called injective if for every x and y in V, we have phi of x equals phi of y, implies that x is equal to y. It's called surjective if phi of v equals w, and it's called bijective if it's both surjective and injective. The first property, being injective, in real space means that the function phi passes the horizontal line test. Surjective in real space means that the set of points that the function maps to is the entire range. Injective can be thought of as one-to-one, and surjective as onto. Keeping in mind these three definitions, if phi is surjective, then every element of W, that's the target set, can be reached from V. That is, there's some element in V that reaches every element in W. If phi is bijective, that more or less means it can be undone. So that means there's a mapping that if phi of x is equal to y, there's an inverse function that we can apply to y to get back x. Some special cases of functions, taking advantage of these definitions, an isomorphism is a function that maps set V to W that is both linear and bijective. An endomorphism is a mapping from V to itself that's linear. An automorphism is a mapping phi from V to itself that's both linear and bijective. An example of a linear mapping is given by the mapping phi from R2 into the complex numbers, given by phi of x is equal to x1 plus x2i. Here we notice that if we take two vectors, x1, x2, and y1, y2, phi of x1, x2 plus y1, y2 is equal to x1 plus y1 plus y2 plus x2i, and that's equal to x1 plus x2i plus y1 plus y2i, which is phi of x1, x2 plus phi of y1, y2. Similarly, if we multiply a vector by scalar lambda, the lambda pulls right out. So this justifies why we sometimes talk about complex numbers as if they were ordered pairs in R2. There's a bijective linear mapping that converts the elements in R2 into complex numbers using element-wise addition and normal addition with complex numbers. Here's a theorem. A finite dimensional vector spaces V and W are isomorphic if and only if the dimension of V is equal to the dimension of W. This states essentially that there exists a linear bijective mapping between two vector spaces of the same dimension. Intuitively, this means that vector spaces of the same dimension are essentially the same thing, as they can be transformed into each other without incurring any loss. Now consider vector spaces V, W, and X. Then a linear mapping phi from V to W and psi from W to X, if those are both linear, then so too is their composition. If phi from V to W is an isomorphism, then so too is its inverse. Finally, if phi from V to W and psi from V to W are both linear, then so too are their sum and scalar multiples. The notation gets a little bit tricky, so we're going to let capital B, unbolded, be the set B1, B2, all the way to Bn, and that's going to be an ordered basis. We're going to let B star be a set B1, B2 through Bn, and that's going to be an unordered basis. Capital bolded B is going to be the matrix with basis vectors as columns. So if we let B be an ordered basis for vector space V, for any x in the vector space, we obtain a unique representation or a linear combination where x is equal to alpha 1 x1 plus alpha 2 x2, so on, up to alpha n xn. Here, the alphas are going to represent the coordinates of x with respect to the basis, the ordered basis V, and the vector alpha, alpha 1 through alpha n, in n-dimensional space, n-dimensional real space, is the coordinate vector of x with respect to the ordered basis V. Basis effectively defines a coordinate system. We're familiar with the Cartesian coordinate system in 2 dimensions, which is spanned by the canonical basis vectors E1 and E2. E1 being 1, 0, and E2 being 0, 1. In this coordinate system, a vector x in R2 has a representation that tells us how to linearly combine E1 and E2 to obtain x. However, any basis of R2 defines a valid coordinate system, and the same vector x from before may have a different coordinate representation in the different basis. In the figure here on the left, we see a vector x in the standard canonical basis with basis vectors E1 and E2. The representation of this vector is 2, 2. However, with respect to a different basis, call it B1, B2, the same vector will have a slightly different representation. In this case, x is going to be 1.09 B1 and 0.72 B2. For an n-dimensional vector space V and an ordered an ordered basis B of V, there's a mapping phi that takes n-dimensional Euclidean space into V, and phi of EI is equal to BI. It's a linear isomorphism. And here, when we talk about EI, we're talking about the standard basis in n-dimensional space. Now we're ready to make an explicit connection between matrices and linear mappings between finite dimensional vector spaces. Let V and W be vector spaces, and B and C be the bases corresponding to V and W respectively. We'll take phi as a mapping from V to W. For J, an integer between 1 and n, phi of Bj equals alpha 1j C1 plus all the way up to alpha mj Cm, or the sum of alpha ij Cj, where I runs from 1 to m. This is a unique representation of phi of Bj with respect to C. We call the n by n matrix A sub phi with elements A sub phi ij equals alpha ij, the transformation matrix of phi. We use the transformation matrix to map coordinates from one basis to another. We'll let B be the basis 1, 0, 1, negative 1, and C be the basis 0, 1, 1, 1. If we want to make basis vector B1 as a linear combination of basis C, we end up with negative C1 plus C2. And B2 we find to be negative 2C1 plus C2. Therefore, if we want to switch from basis B to C, we use the change of basis matrix negative 1, 1, negative 2, 1, where the first column of S is the first coordinate vector of B with respect to C, and the second column of S is the second coordinate vector of B with respect to C. So building on that example, we'll let B be the basis 1, 0, 1, negative 1, and C be the basis 0, 1, 1, 1. We found our change of basis matrix, S, negative 1, negative 2, 1, 1. And we'll take a vector A, 0, 3, in R2 in our standard basis. Now, if we want to put A in terms of basis B, A is going to end up being 3 times basis vector B1 minus 3 times basis vector B2. So vector A in terms of basis B is 3, negative 3. Now we can go ahead and figure that out to put A in terms of basis C in the same way, or we can use our change of basis matrix and say that our new A in terms of basis C is going to be our change of basis matrix S times A in terms of basis B, or negative 1, negative 2, 1, 1 times the vector 3, negative 3. And we get that that's the vector 3, 0. So 0, 3 is in our standard basis. 3, negative 3 is the same physical vector in terms of basis B, and 3, 0 is again that same physical vector in terms of basis C. What we have in this diagram is a set of vectors shaded from yellow to green to blue in the shape of a square. That's our original data. And what we do is we're going to apply some transformations to that. So if we take the original data and multiply by A1, we get a rotation by 45 degrees. So any vector, of which there are 400 of them in the original data, any one of those multiplied by A1 would rotate 45 degrees counterclockwise. In figure C, we've taken that same data, that same A, same set of vectors that are in A, and we've stretched them. We've doubled the amount of X coordinate that they take. Our third one is a combination of reflecting, rotating, and stretching. So we can see that taking various matrices and multiplying vectors by these matrices will actually move the vector around. In our next video, we're going to dive a little bit deeper into this idea of changing bases.